Okay, let's dive right into this explainer. Today, we're looking at an absolute masterclass in marine engineering, focusing on the GF-12000 drillship. Now, we usually think of massive ships as having one static shape, right? But the premise we're exploring today is that the GF-12000 is essentially a shape-shifting vessel. Same ship, three completely different postures in the water depending on exactly what she's doing.
Just to give you an idea of how dramatic this physical shift is, take a look at this number on the screen, 11,500. We're not talking dollars or miles here. That is exactly how many metric tons of seawater and heavy gear get pumped into and stacked onto the ship. And the key phrase there is on purpose. It's a massive physical transformation that happens right out there in the open ocean.
To put that into perspective, because 11,500 metric tons is kind of hard to wrap your head around, that's roughly the weight of 100 fully loaded Boeing 747s, literally added and removed on purpose. And all that weight, it pushes the vessel exactly 1.5 meters deeper into the ocean when it switches from just sailing across the water to actively drilling a well.
So let's look at Section 1, Transit versus Operating Modes.
Since a drill ship of this caliber essentially has a dual identity, we need to quickly touch on two basic naval concepts. First is draft, which is just the vertical distance from the keel, the very bottom of the ship, up to the waterline. And second is displacement, which is the total weight of the water the hull pushes out of the way. Basically, the draft tells you exactly how much weight the vessel is carrying, and it dictates how she's going to behave when it comes to stability, motion, and thruster load in any given mode.
When we contrast these two primary modes directly, you can see that in transit mode, when she's just sailing to a location, she rides high and light at a 9.5-meter draft, displacing 65,500 metric tons. Transit is all about favoring a minimum draft because less drag means more speed. But when she arrives and shifts to operating mode, she sinks down to an 11-meter draft, displacing 77,000 metric tons. That's because drilling requires absolute maximum stability. And, actually, as a quick aside, there's even a third, heavily ballasted survival draft that exists purely for riding out extreme weather.
Moving on to Section 2, the physics of ballasting.
Now, what's really interesting about this slide is how they actually make that switch. The crew doesn't just load on heavy cargo. They intentionally flood these massive ballast tanks buried deep down in the hull. Walking through the formula, it makes perfect sense. To find your added displacement, you just take your operating displacement of 77,000 metric tons and subtract your transit displacement of 65,500, and boom, there's your 11,500 metric ton difference. That is literally the mathematical difference between sailing light and drilling heavy. Out in the engineering world, there's a really practical rule of thumb used for drill ships of this size. Basically, every additional meter of draft typically adds about 7,000 to 8,000 metric tons of displacement. The crew actually uses this quick calculation to sanity check their complex ballast planning on the GF-12000 before a single valve is opened. It's a vital, everyday check on a seriously complicated mechanical process.
And you have to remember, taking on the weight of 100 jumbo jets is not something you do casually. Uncontrolled ballasting will drastically change the ship's trim and stability in real time, making it an incredibly dangerous procedure if done wrong. So you absolutely have to follow the approved stability booklet. It has to be directly supervised by the master and the ballast control officer, and above all, you never ever rush the transition. It's a slow, highly methodical transformation.
Which brings us to Section 3, buying a calmer ride.
So the crucial point here is why? Why undergo this massive, potentially dangerous operation just to sit 1.5 meters lower in the water? Well, the insight most people miss is that this deliberate sinking is actually controlled buoyancy management. It is functionally identical to what a submarine does during a trim dive. It's just a partial, highly calculated version of it. The drill ship is manipulating its buoyancy to lock itself into the ocean environment, getting ready for the intense work ahead.
I actually want to pause specifically right here and challenge you to think about the physical effects of this. What do you think happens to the vessel's natural roll period? You know, the way it sways side to side in the waves when you push that hull deeper from 9.5 to 11 meters.
Well, here is the reveal. The roll period generally lengthens, and the roll amplitude in your typical sea states actually tends to reduce. Because the deeper draft increases the vessel's effective mass, it fundamentally changes its metacentric behavior. It essentially becomes sluggish to the waves. It stops reacting to every little swell, creating exactly the calmer, steadier ride the drilling operations absolutely demand.
If you need an analogy to cement the concept, think of a pickup truck. Driving an empty pickup truck down a bumpy dirt road means you're going to bounce over every single rut.
But if you load that truck bed full of heavy gravel, it rides lower, it corners flatter, and it resists bouncing. The GF12000 is doing the exact same thing. It's loading the equivalent weight of roughly 11,500 shipping containers filled with seawater, just to resist bouncing on the ocean waves.
And this brilliantly illustrates the physics at play. By keeping the flooded ballast tanks low in the hull, you pull the ship's center of buoyancy down. You're effectively hiding the belly of the vessel from the chaotic, high-energy wave action churning at the surface. It is an incredibly clever manipulation of physics, literally using the ocean itself to stabilize against the ocean's own movements.
To summarize the absolute core takeaway from the source material, this entire massive shape-shifting process exists solely to buy calmer motion for the rigid riser and the BOP stack sitting 1,500 plus meters below. That is the endgame. You simply cannot have a ship heaving violently on the surface when it's physically connected to a rigid pipe and a wellhead on the seafloor. Everything we just discussed is about protecting that critical deep-sea connection.
So, before this explainer, we knew the basic dimensions of the hull. Now we understand her 3 distinct draft conditions, the massive displacements involved, and exactly why she manipulates her buoyancy. But knowing how she sits in the water leaves us with a really massive question. The GF12000 has a huge hole cut straight through the middle of it, called a moon pool. How on earth does this incredibly heavy, deep draft platform make a giant, open, double-hulled moon pool structurally possible without the ship just breaking in half? Well, we are going to dive into the structural engineering secrets of the hull in our next explainer. You definitely don't want to miss that.